will be Rick Egeland, and he will be talking about the rarity of sun-like cycles, and that depends on Rossby. Please.
Okay, thank you. So yes, the sun, the best observed object in all of astrophysics, as was proved in the last talk, looks like a very violent and chaotic place, especially when you're looking at the upper atmosphere. And it's violent and chaotic on these large scales here, looking off the limb of the sun, and on the small scales with the spicules and all of the dynamic motions there. And why shouldn't it be? I mean, it's outer 30% of it is a turbulent convective zone, and I guess you would be pretty chaotic and violent too if you had to live in a place like that. But the magic of the sun is that in that zone, in the turbulent convective region, this well-ordered magnetic cycle comes out. And I think it's spectacular to behold. You have the changing polarities. You have the latitude migration, the polar migration of the flux, all very ordered in space and time for decades. And we presume for centuries that pattern has been ongoing. The question is, what are the physical conditions that are conducive to making such a well-ordered magnetic cycle like that? And we know it very well for one data point. If you have one solar mass and one solar effective temperature and one solar radius and the solar rotation rate, you have the sun, right? And then you get the magnetic cycle. My work looks at other stars that are close to the sun, but varying mostly in rotation period, although there's some variation in metallicity, and looking for the region where sun-like cycles may be present. So I study the activity, amplitude, rotation, and variability of solar analogs, and I'm using 50-year composite time series of calcium HK as my proxy for magnetic flux. And this shows the first three of those properties. The center diamond is the median activity for each of these 50-year time series. The extent of the large thin bar is the 98th percentile, the inter 98th percentile range, which is an estimate of the amplitude, the whole amplitude of the calcium for these stars. And the thick diamond, the thick bar is that same inter 98th percentile range over seasonal bins. Okay, so it's a short scale amplitude, and I found that amplitude scales very well with median. It's actually linear with the median activity that's shown on the inset plot. And as we know, the activity decreases with increasing rotation period, and the amplitude also decreases with increasing rotation period. The rotation period is given on the x-axis. For 4 of these stars, it's just a lower limit. There are no rotation period measurements, but I have v sine I and radii that I turned into a lower limit for a rotation period. And just to be warned that there are 4 subgiants also in this sample, and they're mostly on the low activity side. So this is what a sun-like cycle looks like. This is the 100 years of the sun in the S-index. And there's 2 important things about this plot. First, it's very long. And it's uniquely long. We don't have 100 years of observations for magnetic activity of any star, and except for the sun. And that's thanks to the Kodaikanal data that's shown on the bottom, where they took calcium spectroheliograms, turned them into a plage index, which was then calibrated to the NSO SAC peak calcium observations and tied it together to make a 100-year time series. The second important thing about this is that it's on the S-index scale, which is used by Mount Wilson Observatory. And that's an instrumental scale that is defined by the HKP2 instrument. And those are the red points in cycle 23. So all of the SAC peak data is calibrated using coincident observations, which has lowered the estimate of the solar median activity by between 5 and 9% based on previous estimates that didn't have access to that coincident data. So the amplitude of the cycle is about 8.6% in calcium. And the sun-like cycle, if you take a periodogram of it, looks like this. And the thing to note here is there's only one period that matters, and it's the 11-year solar cycle. The lower frequency variation is a reflection of the fact that not all of the cycles have the same amplitude. So you have to have some more Fourier components to account for that. And the roughly factor of 2 is a harmonic that's telling you that you don't have exactly a sine wave shape. But I'm also interested in the quality of it. And I've come up with this measure that's called the normalized amplitude, which is roughly what fraction of the variance in this signal is explained by a sine wave at that period, okay? So Pn is just the power of a periodogram peak, normalized in the way Scargill would have done, or in Horn and Baliunas. And you just take the square root of it with respect to the number of observations, and you get the normalized amplitude, which is basically a measure of how close you are to a sine wave. If it's 1, it's a pure sine wave. It's a pure sine wave. So the sun has the best, the highest normalized amplitude. It's the highest quality cycle in my sample. All of the other stars have somewhat less high quality, and it's obvious by looking at the time series. They're all faster rotators, and actually the majority of my sample looks like this, sort of erratically variable. There are statistically significant periods in here, but there are multiple of them, and the sun doesn't behave like that, or they're very flat, like the HD 9562 on the bottom. This is also not a sun-like cycle. It's close, but no cigar. But it is very interesting. You have this secondary period in there. And it's at about 2.6 years, and it's very persistent. I mean, you can see it right in the time series going throughout. The sun also has higher frequency variability, but it's really, you have to sort of look into the residuals. You take the cycle out, look deep into the residuals, and then you can see, some significant periodicity on faster timescales. But for this star, the secondary cycle is comparable in amplitude to the main cycle. This is the most sun-like cycle of the stars in my sample, but what is it? This is a binary HD 81809 with a separation of 0.5 to 0.3 arc seconds. So most of the times it's observed convolved. In fact, in this time series, it is observed as a convolved object. Duquesne and Mayor, 1988. So it's a visual and a spectroscopic binary. They did some work to deconvolve the spectra, get some radial velocity curves. It's got a 40-year orbital period, by the way. Large separation, so we're not worried about the tidal interactions affecting the dynamo or anything like that. But the question is, which one is it? So he had a 1.5 solar mass primary and a 0.8 solar mass plus or minus 0.2 secondary that looked like a K-star, right? And since its slow rotation period measured from this time series of 40.2 days agreed with what a K-star ought to behave like, it was assumed that it's the secondary K-star that is responsible for this variation. It fits with all the activity-rotation relationships and so on and so forth. But now I've looked a bit deeply into this, and I'm convinced that it's the subgiant that is responsible for this cycle. And I invite you to look at this paper for all the details. What I've got to put this story together is resolved two-color photometry from Tycho. So I get B minus V for each of the components, and they're both exactly 0.65, just like the sun. One of them is much more luminous than the other. I use the Gaia parallax to get their luminosity. And if I do the trick of using the V sine I measurement, which is dominated by the subgiant, use my radius and calculate the rotation period, I get 42 days plus or minus a huge error that's dominated by the V sine I uncertainty, which I have reason to believe is a bit pessimistic based on other studies. But that basically points that the primary has the same rotation period as is measured in the calcium. Therefore, the thing responsible for the calcium is probably the primary. There are other arguments based on ensemble studies. That blue curve shows you the expected rotation period, activity rotation relationship from Mamajek 2008 for the secondary component, and you find that if it was at that 40-day rotation period, it would have a really low log R prime HK. I do some work to deconvolve the S index, and I find that the story where HD81809 is responsible for the cycle is consistent with the ensemble behavior, but the contrary case is not. So I find the solar cycle is exceptional. Basically, only 5 out of the 26 of my stars are sun-like in the ways that I've mentioned. Like that's no significant secondary period, and a high normalized amplitude, which I modify a little bit, giving a punishment factor for very long cycles. So where are the sun-like cycles? This plot shows it to you. The green shaded points are the high-quality cycles that look like the solar cycle. If there's a cross through it, there was a detected in Baliunus 95, a secondary cycle. And you notice that it's mostly K-stars that had the high-quality cycles in this study. And this is representative of most of what we know, although we're going to have new results from Hall very shortly, so look at his poster. This just goes through some of the statistics of it, and I want to say that of the high-quality cycles, excellent and good, 81% of them are from the K group. So what does the sun have in common with those stars? Well, it's the Rossby number. So I went through the literature, looked for rotation periods for all of these stars, put them on this diagram, and you come up with the hypothesis. For G and K type main sequence stars, sun-like variability happens only if the Rossby number is large, that is relatively slow rotators. So there the sun is with all of the K-type stars. The exceptions are up there on the left, have been determined as complex cycles by Ola 2016 based on their time frequency analysis. I believe those need a closer look to see if in fact they are in some sense different than the sun. A quick advertisement for sunstardb is a publicly accessible database of observations. You could make all of the plots I just showed you using sunstardb, and I invite you to take a look and contribute to this database so that we don't have to all go hunting through the literature for everything. And with that, this is my conclusion.
Thank you very much, Ricky. Questions? Please, in the back.
Lovely work. So you mentioned...
Can you please identify yourself?
Surbani Basu, Yale University. You mentioned earlier in one of your first or second graphs that you have sun-like stars, but they differ in metallicity. Do you see any metallicity effect? Because at a given temperature, a high metallicity would be a deeper convection zone, so it'll affect your Rossby number and everything.
Mm-hmm. I haven't looked for an explicit effect from metallicity. Most of them the ones that have a large excursion are low metallicity. So it's sort of in the other way. I don't have I think only one that's a little bit higher than solar metallicity, but right, that's right, something to look for.
So in the Emre Işık from MPI for Solar System Research. Emre Işık. So these all are complex cycles. As far as I remember, many of them showed multiple periodicities, right? So in several of them, I think it's possible to have the secondary longer time, longer period component could be due to these amplitude fluctuations. What do you think about that?
Which amplitude fluctuations?
I mean, longer term amplitude fluctuations of the cycles themselves. Like the solar cycle amplitude fluctuations in the long term.
Yeah, right.
So in these multiple cycles, one should be careful, I think.
Yeah, except, I mean, this, like, look at 20630. That's more than an amplitude. I mean, So you might say there's this 5-year cycle. You look in sort of the middle of the time series there, and there's a variation. There's a peak at that one. But if you're going to call the longer one a cycle, which I don't dare based on this time series, I don't believe that it's going to repeat like this. And that's the definition of a cycle. I would say it's more than just an amplitude fluctuation of the cycle. It's really something else, I think.
Okay, if I can ask a short question, I mean, when one looks at the S-index time series of the sun, the last minimum, 2008, I mean, was 250 days without sunspots. There were times with no plage in it. And yet, when you look at the S-index, it seems to be almost higher than the previous minimum. I mean, what is your explanation for that?
Higher than the previous minimum? I
Among,
don't think it
among
is.
friends.
No, I don't think it is higher than the previous minimum
But
within
it's
the
not,
uncertainties.
it's not lower.
Yeah.
All right, Mark, last question.
Oh, maybe it's a bit vague question, but in the solar data, you're not really measuring the S-index the way it is measured in the stellar data, and so you're doing a conversion. And do you think there could be some other technical or other issues in the sense that you're not actually observing the reference bands in the solar data that are used for the S-index? Do you have any thoughts on that?
Well, in the red points, I believe that we are, because those are measured by the Mount Wilson HKP photometer, basically reflected sunlight off the moon. So it's the same instrument that was used on the stars. And then the name of the game was just to calibrate the sun as a star observations to that. And did the best I could, took into account the uncertainties, and
Okay, maybe this is something that you can discuss during the lunchtime, and I will also talk to you during lunchtime.
Okay.
Anyway, I suggest we thank Ricky for the talk.